waste time fixing it themselves. So all of these things will combine together. So we think this is a big deal. I mean, we think it's very important. So at applications level, we have some things embedded in this that allow you to do graphics properly, the PostScript interpreter stuff. Everybody's writing their own PostScript interpreter. That's just fine. Get the books from Addison Wesley, read them, write a PostScript interpreter. It changes the way we move graphics around the world. And the operating system converges, and you've got all the networking. So if we can use this chip to replace proprietary computer systems, well, watch this space. We'll see if this happens. We believe this is, and I think these announcements show, this is the next major Unix platform. So this just shows that if you use some spurious cyclical analysis, every 5 years things change. Well, 72 to 77, PDP-11s, 77 to 82 VAXs, 82 to 87, 68,000, or let's say 386 style machines. Each of these increases in that user interface, the display, in more and more powerful ways. And at this point, in 87, 88, we're going to change the CPU technology again, and we're going to change the display technology, because the eye is the most critical element of this. So we're transitioning to these, quote, super workstations that are fast. Okay, so what this goes through, what the RISC architecture looks just like, very much like the Cray architectures. Single cycle execution, lots of registers. We can go through this in detail for those that like to talk about how this works, but in particular this adds tagged architectures for Smalltalk and for Lisp, so that there's great speed-ups for these object-oriented, more powerful languages that a lot of things will be coded in. We need new languages. We need new graphics. We have to get to high-resolution graphics so you can see things. Photographic quality. And anyone, we all watch television, to go from an environment where a lot of information comes to us on a screen to an environment where we have ugly characters on small screens is just not acceptable. And there's no reason to continue doing it except if you're locked into a vendor that can't do better. Well, we want realism on the screen, and that makes these machines used by wider and wider groups of people. We have to take all the existing environments, the Chem Abstracts one's a good example, or Mead Data, or a variety of any of the providers of information who have incredible resources and know what that data is in ways no one else does. How do they present it? Well, they had to make their own homebrew stuff over the last 10 or 15 years. It's now time to move it forward rapidly and to make major jumps. And if it doesn't move forward rapidly, other people will do it. They won't have the data, but they'll have the way of presentation of the data that will make all the difference in acceptability of these products. So I think I'll skip through, since I've discussed what Spark is. This just shows the speeds. Here are the people making the ones right now. You can call them up, go buy this stuff. You can touch the Cypress chip. The bit chip is not in silicon yet. But you can go license it. And you can license the operating system that runs on it. And right now, Fujitsu has at least 40, it seems to me more like 60, design-ins with this chip. Citicorp was one I mentioned. There are a bunch more. So it's a 32-bit machine. Okay, I will skip over the details of the architecture. Note only that since it's simple, that's what allows it to be made easily by people. Highly pipelined. So this means that this exponential chart continues, and that's the fact that has great implication for all the work we do in software. That's the chip from Fujitsu. There was a board level design in which vanished. And so here are the speeds these things will go. Double them every year. So this is all fairly obvious. Now what happens after that? Well, we have a variety of technologies. No one still knows the full implications of well, we're moving switching speeds down. Bell Labs can now switch not, the Cray switches at what, 7.5 nanoseconds. Picosecond switching time devices are around, and optical switches at Bell Labs now are in the 50 femtosecond range. So we're getting down to And these are orders of magnitude, many orders of magnitude increases in switching speed. Can you build a computer out of it? Open question. That's what we're working on. But nonetheless, we have tremendous technical increase, and we're still in the uniprocessor world. I'm not yet talking about connection machines or hypercubes or a variety of other specialized multiple processor architectures. The very long instruction word devices we believe you'll see a lot of soon. Essentially, write a compiler that takes your code, puts it into 200-bit wide microcode, and runs it fast. Multiple instructions executing in the same clock tick. We're going to see a lot more machinery like this. And you can build them, as we're letting JPL and other people build hypercubes out of these chips. So we get some uniprocessors built into these meshes because that breaks things. We have to break all of these interconnection networks to learn about how to make them better. Which brings up the graphics point. We believe that PostScript is the ASCII of the 80s. It was nice to have a single 128 character set that you could send to any printer and have it print. Now we're sending PostScript code which describes all graphical objects as high-order polynomial representations of curves. It's like a silkscreen. Draw curves, shove paint through. Well, that's a far more powerful graphic paradigm. Simple graphic model allows you to image anything. Suddenly we're talking about curves, and you extrapolate this, generalize it to 3 dimensions, which is a project we've been working on a lot, and all representations of 3-dimensional objects become high-order parameterized surfaces, patches. Now, there are some domains where you'd like volumetric information, so the surface description is not analytically rich enough to capture all you want. But for many, if you look at Newell's teapot or any of these wonderful graphics that you see at SIGGRAPH, to do that as polygons, 50,000 polygons, nonetheless, no matter how many polygons, has little jaggy lines running around the edges. So the notion of capturing graphic objects in a higher order analytic way is a powerful notion. And there are those that will speak that know much more about this than I do that can describe where this fits into the general evolution of graphics. But our feeling is that everyone wants real-world quality imagery, and that's the power that drives the adoption of Craze in representing complicated environments no one can see today in what's becoming known as the visualization domain. That is, why can't we have a machine on our desktop that's cheap that lets us see into the heart of a chip or the front edge of the space station, a launch vehicle, watch hydrocode. We want to see things because the data flow is far too rich and too rapid for us to understand in any way but graphically. So, if you look at the amount of computing you need to make these fancy displays, moving through the years from ASCII to bitmap to today with polygons, a Silicon Graphics machine makes a beautiful image, lovely stuff. To move up to curves and solids is 2 orders of magnitude jump in computing power, which will come. An example of this might be a lovely machine, the Pixel machine. If anyone went to SIGGRAPH, clearly the hottest machine at SIGGRAPH was this highly parallel machine made by Mike Popmazel. Chuck Surino can give you great detail about this. Stunningly beautiful machine that indicates real-time ray tracing is here. It's time you can put this on your desk. If you want to rotate the chem abstracts, well, it's a 2D representation today. You want to rotate a molecular structure and allow somebody to interact with that to go back into the registry to retrieve chemical information. It's here. You can do it. The speeds, the algorithms, things are here now that allow you to do that. And since it's so much more powerful than existing methods of describing this stuff, it's going to win. So we need some speed. So how do we make these things go faster? Well, we need to do much better I/O. We need to do much higher level languages, object-oriented programs. And so let's just quickly speculate over the next, say, 10 years, 14 years to 2001, on what happens to Unix, to user interfaces, to CPU architectures, and to hardware. And then I'll stop. But this is, what I've been saying is reasonable. It sounds crazy. 100 MIP workstation, 2 years, 2.5 years from now, at the same cost of the workstations that are sitting out in the lobby. Well, that's I think the inevitable logic of what I'm presenting. That's what you'll have. Now, this goes beyond that. Well, we've got to do something about C. Not only do we have this ISO problem, it's just low level. We've got to do something better. The kernel needs to be fixed, and that's beyond my competence to describe how that will work. And we have to do this problem of distributing programs around huge networks, little bits of modular code, concurrency and multiprocessing. Well, these are the territories we desperately need. Anybody in this room that wants to work on this, I can give you a name or two of places to go to work on this stuff, because these have to be tackled. So what do we do? Well, first thing we're going to do is rewrite Unix in C++. That'll give us some object-oriented handling. There are arguments. Carnegie Mellon thinks there's some problems with C++. Doesn't matter. We have to move the code forward so it can be maintained by a lot of people in reasonable ways. We have already concurrency packages, a lot of lightweight process code. We've been giving this to Cray for a couple of years. It's going to sort of slide into a lot of these machines. Actually, we're trying to get Cray to play on the multiprocessor front so that we can get their knowledge about this. The 64 processor Cray 4 has to be able to run a Unix that handles all of these problems well. And we're working on all of these, the user mode level, move things out of the kernel up to user mode, handle concurrency, dynamically relink things across networks. We need to move all of this out of the existing kernel. The kernel is just too big. So that's the direction we're going to move in Unix. We have to fix this ugly Unix look and feel. So we need to do things that do what, my talk is a demonstration of the total failure of the ways that we have today to convey things. I wave my hand up here. Well, it means something to me. It means little to somebody out there. You can't see me to begin with. Where is voice? How do we integrate all these things in some reasonable way? Well, we'll have enough MIPS to begin to work on. Voice input, gesture input. The displays will be routinely 3D. And routine animation. And I can't emphasize the animation aspect. Well, the best way to illustrate it is at the Cray Scientific and Engineering Conferences that they have every year and a half or so. 3 years ago, there were maybe 2 videotapes. I have 500 people in a room. Everybody's computing at all the major centers, and mainly what they're doing is looking at hydroflow, or looking at protein synthesis, or looking at chip design. Those are the domains. All these are graphic. 2 videotapes. A year and a half ago, there were about 8. A month and a half ago, up at Cray, there were 40. Everyone arrived at there was one of these machines, and everyone arrived with a videotape. So that the common desire of all red-blooded Americans to go to Hollywood is actually imminent in all scientific work. You can't understand it if you can't make movies. You want to show it to people. Here's my work. And that's what was happening at the conference. And you'll see at Ohio State, at Illinois, the National Center for Supercomputer Applications, every place that has a machine that makes pictures will have software that allows you to make movies. Move it to video disc. Move it to NTSC, ugly NTSC video. Move it to there's emerging digital video is a big topic. There's emerging ways to represent high-quality images and replicate them and send them to your friends. It's home movies for those of us that want to send our imagery around to people, and it'll be in the computing environment embedded. So routine animation is very important. We will support all the PC look and feel, the OS2 presentation manager stuff. If Apple would get off the tack of suing everybody that uses a pull-down menu, this is just ridiculous. Inside News, we implemented Smalltalk, in essence, all the object-oriented stuff. Simple, because the designers of PostScript made these associative arrays that let you build class, object, message passing, all this stuff. So in News, little windows are all implemented by saying, class window, give me a new one, you get an object, you change the methods in it, you change the variables in it. Page and a half of code implements the entire Macintosh window interface. Just changes the methods for the width of the scroll bar. Trivial. Well, that code, I guarantee you, Sun can't do it, Apple will sue us. Right? So some person out there will invent this page and a half of code and put it on the net. And then you can make it look any way you want. The idea is to make things extensible. And we need to put in a variety of higher order user interfaces. And in the CPU architecture, this is Joy's slide about, he likes this joke about run out of gas. That's gallium arsenide. What happens, RISC may run out of gas in 1992. So what happens? What do we do about parallelism? Good question. What do we do about all this existing low-level code in C, Fortran, and Pascal? What do we do on compiles for multiprocessor implementations? Well, we'll evolve machines that are very large instruction word machines. There are a number of these today. They're not commercial, generally. There's some commercial implementations. But you need to have huge, wide instruction words to execute simultaneously. A lot of compiler technology. One instance of this that's interesting to look at is a machine we introduced mainly by buying the company. Nick Englund, who you may know from his Iconis days, formed a company to make the world's hottest single-board graphics machine. We bought his company. And what he's got is a compiler technology that takes existing code, compiles it into this 200-bit wide microcode, and runs it. So it ends up at 20 to 40 megaflops on this board inside the Sun. There's two boards. It's very impressive. It moves up into the Silicon Graphics high-end performance range, it moves up, actually, I'm sorry, it beats that, no problem. It moves up into the Pixar territory, but it doesn't have the richness of software that the Pixar stuff does. But suddenly it begins to look good. It's a very interesting and important board. So we don't know what to do about massively parallel. We have projects at Sun doing this, but this is a long talk. If you go to the Parallel Architectures Conference in, I guess it's March, it's chaired by the guy that's the head of parallel work at Sun, Fddi Briggs, who used to be at Illinois. If any of you have that McGraw textbook on parallel, it's Fddi Briggs' book. So he's at Sun, and if you want to know about that, call Fddi. But we will move some of these applications onto the desktop, and this means we'll have graphics on the desktop. So the resuscitation of superconducting means maybe we can pull Josephson junction technology back off the IBM scrap heap and put it into a computer. This would be great if we can do this. This is Joy's dream. It's always been his dream to do this. So we'll see. We don't know yet if people, you're all following superconducting. Can you make a wire out of these ceramics? Who knows? But that's something to watch carefully. And we ought to be able to get down to picosecond gate delays. Picosecond gate delays means 3 orders of magnitude, 4 orders of magnitude over existing computer technology. This is desktop speeds. And to think about this, the way you have to think about the software development environment, use it relative to, here's some numbers, right? Superconducting multiprocessor, 10 picosecond cycle times, 100,000 MIPS. Now, RAM technology is coming right along. If you put 1,000 gigabit RAMs in, you end up with 128 gigabytes of RAM. Well, let's stop worrying about all these swapping questions. Stuff's cheap. So, and something actually to consider, and it's a problem for people like Ford or other people that have huge design files in Fortran 4 with 16-bit integers. We're moving to a world of 64 bits. That's just clear. So let's start thinking about where do I store, if I do have to take all my existing data files and turn them into 64-bit wide, I've got them in 16-bit. Yes, is the answer. You have to start thinking about this, because the network technology and the storage technologies and the existing huge, the important parts of the data, these things have to work together in nice ways. You have to plan transition strategies for existing data into these new large networked computing facilities. We have this little marketing slogan, the network is the computer. We have to think about this service provider of the network giving you enormous specialized algorithmic computational power, data storage. You have to think about making these things work together. So some of your time has to be spent paying attention to these very boring standards meetings. But this is the direction things are going, and it means for a display for you, a 4,000 by 6,000 display. Well, 75 millimeter film is about 4,000 by 4,000. 4,000 by 6,000 display, 24 bits deep. Well, make that 32. Put some opacity and other dimensions in. Stereo times 2. Right? Stereo. You have to have stereo if you're going to look at molecules rotate. And 24 frames a second. Well, how about 30 frames a second? All right. So there's a number, that 4,000 times 6,000 times 24 times 2 times 24. Increase it by a couple of factors here. We end up with a data rate to get an image at that resolution and quality of 30,000 megabits a second. Well, where do we stand in networking technology? Ethernet crumbles. What do we do here? Well, part of it is you send images as PostScript definitions so that they don't narrow bandwidth, execute at the rendering device, interpret that PostScript code. That helps. Trivial to implement CCITT group, do the group 4, group 3, group 4 fax standards. Trivial PostScript to do that. Compress images, look for redundancies. Any trick you can play to reduce the bandwidth needed to move images around, that we will play. And we move on from Ethernet to Fddi. Every workstation will have Fddi in it, so you'll have 100 megabit plugins, follow exactly the path Ethernet took. We used to charge $3,000 a board for an Ethernet board in 82 and 83. Then we got silicon, stick it on the board, bundled, standard, cost $20, $15 to us, something like that. Fddi, we have a couple of boards now that implement Fddi. It'll follow the same 2 or 3 year path. We hope 2 year. We should get first silicon maybe, I hope maybe March or April. Put Fddi standard in, and you've got 100 megabit to each workstation. I should stop. Right, okay. And the end of all this is, here's what we think about. If you run a program on a VAX for an hour, it'll take a 30th of a second. If you run a program on a VAX for a year, it'll take 5 minutes. That's the kind of shift in headroom that you have to think about when you're designing your future algorithms and data acquisition and provision and the environment that you're going to design. So you have to, I think it's this arithmetic, just the thrust of it. Quantity in some ways means quality. And so software should depend upon, our work should depend upon open systems, because that's what's going to ride above these inevitable changes. We think that Unix on the SPARC chip is a fundamentally important choice for people to consider in what they're up to, with all the DOS and OS2 stuff playing right along. We think we'll have all these machines that go fast, that then you'll begin to do new applications on, because there'll be something to run it on. You can actually edit in Arabic and in Greek and cut and paste and do things in a multilingual international way that you can't do today. And we'll have a lot of advances coming along behind that that will enable us to dramatically change the environments we have. So that's it. That's what I wanted to tell you about. And if there are questions, I'd be happy to answer questions. Yes, question. That's right. The 3D is not there in the existing software standard. For the last year, we've said to John Warnock and Chuck Geschke, let's all work together so we can do this. There are a lot of ways to do it wrong, and they know how to do it right. I mean, they're the right people. The commercial environment, Jobs, about a year ago, Joy went over with Gosling to Jobs' house and said, look, why don't you take the new stuff, we'll give it to you. Put it on your machine, the next machine, because it's going to be a good machine, could be a good machine. Sure, said Jobs. Well, you know, months went by, typical Jobs. I didn't have a hand in designing it. Jobs, you're not competent. Yeah, I didn't have a hand in designing it. I'm going to do something different. He went to Warnock and Geschke, signed Adobe up to write a PostScript interpreter. At that point, the 3D extensions, which you're all talking about and how this could work, suddenly there's this commercial problem, compounded by the fact that since we wrote our PostScript interpreter from scratch, Gosling wrote it from the spec, anybody can license it from us, anybody can use it. People have started to put it into printers. This is bad from Adobe's commercial point of view. And so suddenly this warm and friendly, I mean, Adobe people are the right people on fonts. They know more than anybody. They're just, that's world-class stuff. To get the 3D extensions done properly, suddenly the lines of communication were not as open. Then they've run into the problem, which is, namely, moving the PostScript interpreter from a printer into a operating system environment where you've got, well, as an example, the printer PostScript says, I'm going to work on this 2,500 dot per inch photo typesetter. A lot of memory. The interpreter runs, builds the images, shoves it out onto film, give me the next one. On a screen, you have 30 of those. Garbage collection. I build an image, whoops, I'm wiping it out. I had it in memory here. Who goes over and recaptures that memory? These are operating system problems. Lightweight processes. You need this to track. There's no input-output in the PostScript standard. You have to extend it to say, okay, there's a mouse. You know, there are all these devices that have to be sending things in. You have to have these threads of control throughout all the programs. So we wanted to give all that to Adobe, but anyway, the line stopped. So now I think we're back on track, although I don't know. But all these questions about projection of 3D objects onto on a 2D surface, how does PostScript handle all this? With this AT&T announcement, since we've embedded PostScript into System 5, it's clearly in Adobe's economic interest to be sure that this works right. So these are ongoing discussions. Call up John Warnock and say, users demand to know. It's got to be done right, and it is possible to do it stupidly. And so they are wonderful people and extremely smart. And we just hope that the business models don't clash enough to keep people from working together. A lot of the good 3D stuff is actually done at Evans and Sutherland, and so we're trying to integrate that all. If you know a lot about this, call Gosling up. The algorithm at Sun is simple. You want to send something to Sun on ARPANET or whatever network you're on. It's the first initial of the first name, like Gosling is J, James Gosling, W, Joy, and it's the last name, so it's jgosling at sun.com, wjoy at sun.com. The guy that's the vice president of software is named Eric Schmidt, eschmidt at sun.com. Dear Eric, do this right, please. And I solicit this because it's vital that we all hear this. It's so easy to make dumb mistakes. And this story of rapid growth means real agony for us. We keep adding things. We just formed a graphics division about 3 weeks ago, or 4 weeks ago or something. So all people are moving and going from here to there, and it's chaos, and we're going to, we're 5,000 people now. We're going to be 8,000 or 9,000 people by the end of the year. Who are these people? So by the time you find out who your next door neighbor is, you have not spent time on getting the algorithms right. So we need all the help we can get. Question? The question is, what about advances in very new orders of magnitude graphic representations? And the citation was to an MIT Media Lab holographic project. The stuff at the Media Lab, Nicholas Negroponte and all the people out playing, Minsky and Alan Kay out there at the, let's go do things that are really very different. A lot of Sun machinery. I'd say by far the majority of the machinery in there is Sun. And the piper that pays are perhaps 20 large industrial organizations. Fujitsu gives them money, and CBS gives them money, and we sell them machines. I mean, we're a cheap operation. We extract money from, but we cooperate with them and spend a lot of time there looking at what they're doing. And there's some people in LA with some very pretty, and in New York with holographic stuff. Yes, we're trying as best we can to track that. We fall behind because the bandwidth is not adequate. We can't keep up. So the notion is to make the mathematics generalizable enough so that the output devices can use it automatically. So that's the dimension. Get the mathematics right, get the notation, get the thing general enough, and you can ride through these new technologies. There's some 3D display techniques with polarized, with laser light that the GM wants to, want to walk into the room and see the smooth surface model of the next car projected, and they've got something like that now. And that's, yes, we're playing in that territory. I don't know enough about it. In this, I guess the person to ask most about this would be either Bernard Puteau, who's our new VP of Graphics, P-E-U-T-O, but he's new, or Wayne Rosing. Rosing's the Vice President of Advanced Development. Rosing was the guy that was the Chief Engineer for the Lisa. And Rosing's doing a lot of the multiprocessor work. He's doing all the CD-ROM, CDI work with Philips. We're doing all this big CD-ROM project with Philips, authoring systems. And he's doing all of the video, digital component encoding video, all the video input. As a typical computer company, we're completely stupid about tying to NTSC. There is a broadcast standard. Why can't computer companies read it and do it? So Rosing's the person that knows about the more advanced display systems. We'd love to get rid of tubes if we can. That's the next round. There was a question over here. In March and April, we'll attempt to stand up and look extremely coherent and say, here it is. Here's the look and feel. In reality, running around right now are groups at Sun, because in this contract, we define the user interface, the look and feel of Unix. Well, of course we do it in concert with AT&T guys. Everybody's got an opinion. And it's bollocksed a bit by this Apple propensity to sue. I just think it's crazy that somebody that would look at what the Alto did and what Xerox did could possibly claim in court that they own pull-down menus. This is lawyer impedimentia. But in any case, it'll look a lot like that. I'd love to put the Mac interface. What it'll look like, presentation manager, luckily Gates, being incredibly clever, went down to Apple and got this deal with Apple that he can make stuff that looks just like the Mac interface and not get sued. So the presentation manager stuff, which is embedded in the SAA architecture of IBM, embedded in but not available yet in OS2, is okay. It's not great, but it's at least got all that stuff in it. So do that. I mean, I think it's quite clear. We'll do the presentation manager. We'll add in this basic environment to Andrew stuff that IBM's now putting out from Carnegie Mellon. We'll do as much as we can of the Mac interface, or just put the hooks there so you can, with a page and a half of code, do the Mac interface, so that if you're an application writer, you can just stick it on there and it'll look just like it's running on a Mac. I mean, it's really quite trivial to do. So that's our answer, is to give a toolkit that the fundamental problem we have is that we have different kinds of users. If you are a seismic analyst with that data I was showing early, you don't care about, I mean, if you're attempting to rotate a molecule in 3 dimensions and point to the insertion where an enzyme is supposed to click, you have a problem not tackled by the Macintosh user interface. I mean, we're going to try and be as coherent as we can to put a very consistent set of user interfaces so that application writers can do just what you say, is to write applications that draw upon a common vocabulary. And then if you want to add something to it, because your specific data requirements make it important, you as someone writing the application code, trying to reach a user audience, have to consider, do I need to go out and invent something extra? So yeah, all the parts about here's what you do, stick to these, is there. I mean, that's the goal. So now, whether we're going to do a good job on this, you have to come March or April. Because I go back and I ask people questions about precisely what, and I get different answers. So it's mail to, let's see, James Gosling. You know, yeah, we understand the problem. Sometimes I